So, first thing we're going to do to solve this problem is we're looking for the acceleration. And we remember we have the net force in the x direction equals mass times ax. Net force in the y direction equals mass times ay. And so we can create a free body diagram for both objects and create some expressions for the net force. So we know both blocks have a normal force pointing straight up, and we're going to, as we normally do on an incline, realign our x-axis to be in the direction of the incline. That way our normal force points up, and our gravity for A points down and to the left. And now we're going to call this theta A. This is going to be theta A, and this will be theta B. Just because that way we can keep this very general. We can solve for the general solution for this setup, and at that point we can plug in our variables. Now, since we are solving this very generally, you have the ability to, on the homework, just write down the final equation, plug in all the numbers, and just put in an acceleration value, right? You could do very little work, but that is not the correct way to solve this problem. You are required to do the free body diagrams, find the expressions, and you have to also follow through and do all of these steps, these algebraic steps. They're very complicated, and so I'm going to go through the same steps you guys will have to go over just to make sure that it goes smoothly, because it is pretty tough. So your setup should be very similar. Maybe instead of putting generals, you could put like 51 degrees instead. But going through the general solution can be a little bit easier. So let's label all our forces. We have the force of friction, remember? Normal force and tension. So there's 4 forces acting on this block. And block B, remember we're going to do theta B, has tension, pulling it back, as well as friction, pulling it back. And then let's call this gravity force. You can call it Fg, but remember the force of gravity is the mass of the block times gravity. So we're just going to write mass of A or mass of B times G. That's what we're going to put for our force. And so we know the next step we're going to want to do is write the net force in the x direction equation, net force in y, and we're going to want to do that for all 4. But for this problem, that's actually not going to be very helpful just yet. We want to try and figure out a new expression for the normal force and the friction force. Let's remember normal force is what? It's sort of like a reaction force from the incline. The incline pushes back. And the incline only pushes back the same amount of force that it's sort of pushing down, right? So normal force normally makes it so that net force is 0. And if we think about this problem, we do have an acceleration to the right? We have an acceleration to the right. That means the net force in the x direction is mass times acceleration. What about the net force in the y direction? Is there a y acceleration? Well, no. The blocks stay on the incline. They never lift off the incline, and they can't go into the incline because blocks aren't really colliding or smashing or being destructively interfering. There is no acceleration in the y-axis, and our net force in the y direction is 0. And when we take our net force y equations, we get 0 equals, well, normal of B minus mass of B times gravity, and we want the y component. And so if this is our theta, cosine will give us the y component, cosine theta B. And we can do the same thing for our left free body diagram. And we can bring this term, I'm not going to write it out again, we can add that term to both sides and just bring it over to the other side of the equal sign, right? So the normal force of A is the mass of A times G times cosine theta A, and the same thing goes for the normal force of B. And this is our general form solution. So this is part of what you have to do. You have to go through and derive all of these expressions. You can't really just leap the end of them. We now have a pretty handy expression. The next thing we want to look at is the friction force. Before we go into our net force in the x direction, which is going to be pretty complicated because there's 3 forces in each expression. It's going to be a big equation. We want to sort of iron out a lot of things that we're going to be plugging into it beforehand. So our friction force, remember the equation for friction force is mu times n. So our friction force for this block is mu times n, which is ma g cosine theta a, right? We're just putting a mu in front. And so our friction force for this block, if you wanted, you could put Fa and Fb just to indicate that they're different. I typically will opt to just try and remember that they're different and not indicate so. Just remember, friction force is different for every block. The only force that's the same is tension. Tension is shared amongst both blocks. So now that we've kind of described this, now we want to go into our net force in the x direction expression. And that's going to be equal to mass times acceleration, since we do have a positive, to the right acceleration. So for A, we have tension minus, well, the force of friction, which instead of writing force of friction, we can write mu ma g cosine theta a. Then we also have the gravity component. It's negative, and it is ma g, and we want the x component, so it's going to be sine now, sine of theta a. And that's all of our components. That's our net force expression. And then that's equal to mass, and in this block it's mass A times acceleration. And we could do the same thing for our y-axis. Let's just roll a little bit up to see that. For our y-axis, we have the mass of the block times gravity times sine of theta, since we want that x component, minus tension, minus the friction force, which we found was mu mb g cosine alpha b, and that's equal to mass times acceleration. Mass of block B times acceleration. All right. And so we have 2 expressions. How many variables do we have? Well, we have a lot of variables, but what we want to look at is variables we don't know, unknowns. We know all but 2. We don't know the acceleration, and we don't know the tension. Those are our 2 unknowns. And remember, for every unknown, you need an equation. So 2 unknowns, 2 equations. 3 unknowns, 3 equations. We have 2 unknowns, and we have 2 equations. So we can actually go ahead and solve these like a system of equations. So we're going to solve for the force of tension. We're going to say T equals, and we're going to add both of these 2 terms to both sides. So ma times acceleration plus mu ma g cosine theta a minus ma g sine theta a. This is our expression for t, and we can take this and plug it into our other equation. We can take this t and plug it in here. And yeah, as you can see, the algebra gets pretty hairy, right? It's pretty lengthy. And so that's sort of the work of this problem. The meat of this problem is just being able to do this kind of thing on a test. So yes, you could just look at the final answer here, maybe use that to find your acceleration and whatever and so on. So on a test though, you're not going to get the same scenario. And on a test, you're going to get, a different setup of blocks. maybe both blocks are going to be on the same incline, something like that. And so you have to keep that in mind. So you can't just like write down the final equation and just randomly use it. So going back to plugging in t, now we have mbg sine theta b, and it's minus tension. So we have to distribute a minus to all three of these terms. So we have minus ma times acceleration, minus mu ma g cosine theta a, and this minus becomes a plus now, ma g sine theta a. And then we have the last term, mu mb g cosine theta b equals the mass of block B times A. So this is a very long expression, and you have to be very, very careful about the A's and B's. It's possible that I might make a mistake, right? And so if you have to be very, very careful. Even I make mistakes. Even teachers will make mistakes, right? It's very tricky. So what are we solving for? Well, A. A is our unknown. So we're going to add ma times A to both sides. And we will get, just bringing pretty much every term back down. And so our right side is acceleration times ma plus mb. And so if we want to find what a is, we have to divide everything by ma plus mb. And so we're going to get a equals, and so this expression there's a little bit of simplification going into it. We're sort of factoring the ma and the mb out of both terms, right? Just to rewrite it a little simpler, we're pulling the g outside. This is the expression that you should be ending up with, and you can plug in the variables, values, the numbers, and get an acceleration a value, and that gets you through part A. So now we're looking at how do we find mu. We want to figure out mu when mu equals question mark, when a equals 0. So mu is no longer 0.25 or whatever was given in the problem. Mu is no longer 0.25. It is some unknown we're solving for, and now we know we don't want any acceleration. They're just sitting there. And mu, when we solve for it, well, we can go back to this a expression, and instead of putting a, we put 0 equals mb sine theta b, and so on, minus mu cosine theta b. And you will get this expression. You can plug in all the numbers you have, and your goal is to solve for what mu is. All right, and I will leave that sort of algebraic derivation up to you guys. It's not too bad. You have to be a little bit careful about the way you distribute division. Just make sure you don't, forget any algebraic operations. You guys should be able to figure it out. And if you have any trouble, as always, Thursday's study sessions.